Imagine taking one step and suddenly weighing twice as much. Your feet slam into the ground. Your muscles struggle to lift your own legs. Buildings groan under their doubled loads. And high above us, the moon and Earth begin falling into entirely new orbits. That is what happens if gravity suddenly doubles. To make this scenario precise, let's assume the gravitational constant, g, instantly becomes twice as large everywhere. The masses and sizes of Earth, the Moon, the Sun, and every object remain unchanged at the moment of the change. Chemistry, electromagnetism, and the strength of materials all stay the same. Only gravity changes. At Earth's surface, gravity would jump from about 8 meters per second squared to 19.6. Your mass would not change. If you have a mass of 70 kilograms, you would still have a mass of 70 kilograms. But your weight would double from roughly 686 newtons to 372. In everyday language, you would feel like you had suddenly become a much heavier version of yourself. Standing still would become exhausting. Every step would require lifting twice the force. Jumping would barely work. A person who can jump half a meter today might only rise about 25 centimeters, assuming their muscles can produce the same power. Running would become slower and more dangerous because every footfall would hit the ground with greater force. Falling would also become more violent. After just 1 second, ignoring air resistance, an object would be moving at nearly 20 meters per second instead of 10. After 3 seconds, it would be moving close to 59 meters per second, about 210 kilometers per hour. But humans would not instantly be crushed. Our bones and muscles are not suddenly weaker. The problem is that they now have twice the load to support. Many people could remain lying down, but standing, climbing stairs, or even breathing deeply would become difficult. The heart would have to pump blood upward against a pressure gradient twice as strong. Tall people would face an especially serious problem because the pressure difference between the heart and the brain would double. Animals would suffer in similar ways. Large land animals would be hit hardest because their weight grows with volume, while the strength of their bones and muscles does not keep up as efficiently. Giraffes, elephants, and other big animals could collapse under their own bodies. Small insects and low-to-the-ground creatures would have a better chance. The built environment would start failing next. A building's mass has not changed, but every beam, column, cable, and foundation must now support twice the gravitational force. A structure designed with generous safety margins might survive. One already close to its limits might buckle. Cranes would be overloaded. Elevators would strain. Bridges would sag, and suspension cables would experience double the tension. Tall buildings would be especially vulnerable because they already deal with enormous loads at their lower levels. Some would crack or partially collapse, not because gravity pulls sideways, because the vertical forces suddenly exceed what their materials and joints were designed to handle. Aircraft could still generate lift, but they would need twice as much lift to stay in the air. A plane's wings would need to move through the air faster, become larger, or produce more lift through a higher angle of attack. Many commercial aircraft could not simply continue cruising as if nothing happened. Helicopters would face the same problem, with their rotors needing roughly twice the lift. The atmosphere would change too, although not by vanishing. Air pressure at sea level is the weight of the atmosphere pressing down. If gravity doubles while the amount of air stays the same, the average pressure at the surface would approximately double, from 1 atmosphere to about 2. The air would also become more compressed near the ground. The atmosphere's scale height, the distance over which pressure falls significantly, is inversely related to gravity. Doubling gravity would roughly have that scale height. Air would become denser near sea level, while pressure would drop more quickly as you climb. For humans, this creates a strange combination. Breathing near the surface could provide roughly twice the oxygen pressure, but each breath would require moving denser air, and the body would still be fighting stronger gravity. At high altitude, conditions would become much harsher because pressure would fall off faster. The oceans would respond immediately as well. Water pressure increases with depth according to density, gravity, and depth. Double gravity, and the pressure at any given depth doubles. At the bottom of the Mariana Trench, pressure would rise from around 1,000 atmospheres to roughly 2,000. The ocean surface would not simply drop by half, but coastlines and water levels would readjust. Waves would behave differently, with stronger restoring forces pulling them downward. Storm-driven waves could become steeper and more destructive. Rivers would flow downhill with greater acceleration, carving channels more aggressively and sending floodwater faster through lowlands. Earth itself would begin to deform. The planet is held together by its own gravity, but the rocks inside it are supported by chemical bonds and pressure. Doubling gravity would increase the pressure throughout Earth's interior. The planet would slowly compress, becoming slightly smaller and releasing enormous stresses through its crust. That would likely trigger earthquakes, landslides, volcanic activity, and widespread failure along geological faults. Mountains would be under twice the gravitational stress. The tallest peaks might begin collapsing over long periods, not because they instantly lose their strength, but because gravity would now push them closer to the limits of what rock can support. The moon would not stay where it is. Its current orbit depends on Earth's present gravitational pull. If Earth's gravity suddenly doubles, the moon's existing orbital speed becomes too slow for a circular orbit. It would move into a stretched elliptical path, reaching its current distance at the far end of that orbit before falling much closer to Earth. The moon would speed up as it approached. Tidal forces, already responsible for ocean tides, would become dramatically stronger. The exact tidal increase depends on the moon's new distance, but the result would be extreme. Enormous tides, powerful crustal flexing, and intense heating inside both Earth and the moon. The moon might survive, but its orbit would become unstable, and its effects on Earth far more destructive. And the biggest orbital disaster would happen around the sun. If G doubled throughout the universe, the sun's gravitational pull on Earth would double too. Earth's current orbital speed is perfect for its present distance from the sun, but it would now be too slow for the new gravitational field. Earth would move into a highly elliptical orbit. At the instant of the change, it would be near the far end of that orbit, then begin falling inward. In this simplified case, its closest approach could be around half an astronomical unit, roughly halfway between Earth's current orbit and the sun. That would be catastrophic. Solar energy increases with the inverse square of distance. At half our current distance, Earth would receive about 4 times as much sunlight. Oceans would heat rapidly. The atmosphere would become unstable. Water vapor, itself a powerful greenhouse gas, would amplify the warming. Earth could enter a runaway greenhouse state, more like a hotter version of Venus than the world we know. Eventually, Earth might swing back outward, but the damage would not reset. Climate systems, oceans, ecosystems, and civilization would already be transformed. So the first moments of doubled gravity would be a physical emergency. People collapsing, structures failing, aircraft losing lift, and oceans and crust beginning to shift. Over days and months, the moon's orbit would change. Over the same general timescale, Earth's orbit around the sun would turn into a climate-ending roller coaster. Gravity feels weak compared with the forces holding atoms and molecules together, but it controls everything large: bodies, buildings, oceans, atmospheres, planets, and orbits. Double that one number and the universe does not merely become heavier. It becomes a completely different place.